Hello everyone, my name is Huong from Pham Mai University in Vietnam. It's a great honor to be here today. Today, I would like to present our work titled Machine Learning Assisted Acetone and Ethanol Classification and Quantification using a PWM-Modulated NQ136 sensor. My presentation has four. Lại đi, lại. Tension in the story. Hello everyone. Hello everyone. Hello everyone. My name is Huong from Pham Mai University in Vietnam. It's a great honor to be here today. Today, I would like to present our work titled Machine Learning Assisted Acetone and Ethanol Classification and Quantification using a PWM modulated MQ136 sensor. My presentation has four parts: the introduction and motivation, the material and methods, the results and discussion, and finally the conclusion and future work. Let me begin with the introduction and motivation. Volatile organic compounds, or VOCs, such as acetone and ethanol, are important targets in environmental monitoring, industrial safety, and medical diagnostics. For example, acetone is a well-known biomarker in human breast analysis, while ethanol detection is essential for alcohol monitoring and solvent leakage detection. Metal oxide semiconductor sensors are very attractive because they are low cost, robust, and highly sensitive. However, they have one major weakness: poor selectivity. Acetone and ethanol are both reducing gases, so the resistance response overlap significantly. This makes it very difficult to distinguish them using a single sensor at a constant temperature. So how can we overcome this limitation without adding more sensors? Our answer is dynamic temperature modulation using PWM. By deriving the heater with a PWM signal, the sensor passes through multiple temperature steps within each cycle. Because each gas has its own absorption-desorption kinetic, this thermal cycling encodes that specific information into the response patterns. Their dynamic responses are nonlinear and high-dimensional, so we use machine learning to extract the hidden information. In this work, we address two tasks. First, classifying acetone, ethanol, and clean air, and second, estimating the gas concentration in the range of 10 to 100 ppm. Now let me describe our methods. The heart of our system is a MQ136 sensor. We designed a custom printed circuit board that integrates the sensor with a signal conditioning circuit and a PWM controller to the driver. This ensures precise and repeatable operation. You can see the schematic and 3D layout on this slide. For controllers experiment, we build a gas delivery system using mass flow controller, propose the gas, target gas, and the carrier air. The mixed gas is introduced into sealed chamber, and a vacuum pump maintains stable pressure and rapid gas exchange. During operation, a microcontroller delivers the microheater with a PWM signal, and the duty cycle is periodically modulated to induce controller's temperature variation. Our datasets were built from 11 independent experimental sessions covering three gas classes: acetone, ethanol, and clean air. Each gas were tested at 5 concentration levels: 10, 25, 50, 75, and 100 ppm. The raw signals were segmented into individual cycles, each with 73 data points. In total, we obtained a balanced dataset of 75 samples, 25 samples per gas class. For each cycle, we extracted 6 statistical features: mean, standard deviation, maximum, minimum, area under the curve, and linear slope. Their feature character amplitude, temporal evolution, and signal energy. All features were standardized before analysis. We first applied PCA to explore the feature space, then used a supervised machine learning model for classification and regression, evaluated under two-paragraph validation. Now the result. This figure shows the raw resistance response under PWM modulation. Its concentration produces a repeatable U-shaped cycle, corresponding to the heating, reaction, and cooling phase. As the concentration increases, the response altitude shifts consistently, confirming good sensitivity to baseline resistance in air, around 750 kiloohm. This varies significantly upon gas exposure. However, and this is the key challenge, the raw profile of acetone and ethanol look highly similar as own concentration. Simple threshold-based discrimination is not possible. And this is exactly why we need machine learning. To reveal the hidden separability, we applied PCA. The first principal component explains 97.2% of the variance, and with three components, we reach 99.7%. More importantly, the 3D PCA projection reveal clearly separated cluster for acetone and ethanol and air. The PWM include features successfully transform overlapping responses into repairable representation. In this figure, we compare 7 machine learning classifiers under stratified two-paragraph validation. Standardization were fixed only on the training data to prevent data leakage. The results are remarkable. LEA and QDA achieved perfect performance, 100% accuracy, confirming that the features space linearly separable. MLP and KNN follow with 7 97.4 and 94.7%. For second task, concentration estimation, we evaluate 6 regression models. Among them, the HRP regressor achieved the best performance. It achieved an R square of 0.992 with a mean absolute errors of only 1.44 ppm for acetone and an R square of 0.9942 with an MAE of 1.4 ppm for ethanol. Also, in this figure, the prediction closely follows the ideal I equal X line. Let me summarize. We presented a PWM-modulated framework that enabled both classification and concentration estimation of acetone and ethanol using just a single low-cost MQ136 sensor. There are three key takeaways. First, PCA saw 99.7% of the variant discapture within three components. Second, LDA and QDA achieve perfect 100% classification. Third, extra trees achieve an R square of about 0.99 with an error of only 1.4 ppm. In short, PWM thermal modulation combined with machine learning transforms low selectivity most sensors into a reliable system for both qualitative and quantitative gas analysis. For future work, we plan to expand the dataset and validate the approach under more complex and realistic conditions, such as gas mixture and vary in humidity. This concludes my presentation. Thank you very much for your attention.